of the Lorentz number and thermal conductivity of a poor conductor. These things I will discuss just after the lunch. Okay, that how CCS is used in performing these two experiments. And one experiment is temperature coefficient of resistance in copper, TCR of copper, and energy band layer of silicon. This also I will discuss tomorrow morning. Okay, so these are the experiments in which we will be using these one. This is how the device looks like. So most important thing is you have to understand the working of a device when you are there in the lab, because in one session you are required to perform 3 experiments also. In one session you will perform the experiment on thermal conductivity of copper, electrical conductivity of copper, and electrical conductivity of poor conductor perspex also. So 3 experiments will go simultaneously. With Stefan's constant you have to perform the experiment on high resistance by leakage. Okay, so this experiment we have a main switch on and off. We have an indicator lamp that simply indicates whether the instrument is on or off. Okay, then we have here in fact 2 toggle switch, high and low. If this is down, so it is acting in the low mode. If it is up, it is the high mode. So in the low mode, the current is controlled by this. This is low current adjustment. So if you are using it in low mode, and the low range, the current will be given by this CCS will be between 100 microampere to 20 milliampere, but in the high range it is 20 milliampere to 0.3 ampere. So depending upon the requirement in one experiment or the other, we have to use this CCS in low or high mode. Okay, so first of all we have to select the low or high mode of operation of CCS. If it is in low mode, we are going to control it by this knob. If we are in the high mode, then we can control by these two. This is for force and this is for fine adjustment of current. Okay, whatever current we just set by using these knobs will be displayed here. Okay, and these are the 2 banana terminals which will give us the current to the required load or wherever we are using. So this is our constant current source. Okay, how to set the current for the experiment? So first of all, I have already explained. First of all, you have to select the range, whether you are going to use a high current or low current. You have to adjust the knob to the lowermost position. Normally you rotate. These are basically several turns they will rotate. So you have to leave it to the extreme left. Okay, and then depending upon the requirement, you have to play with the knob AA dash or B dash. AA dash knobs are for high current adjustment and B dash and B is for low current adjustment. You have to connect the terminal to the output and you can adjust the current to the required value depending upon this. The 3 knobs AA dash B, they can rotate 10 turns. Okay, so these knobs should be kept in extreme left position for minimum value of a current. Then current will increase when the knob is turned right. Near the extreme right knob is turned very slowly. Okay, because they are very delicate. So AA dash can be used for setting the current to a desired value, and the meter will read, the display will read the current in milliampere. These are the range. In low range, it is 100 microampere to 20 milliampere, and in the high position, it is 20 milliampere to 0.3 ampere. Okay, you can do one experiment also to check the load regulation in low current range and the load regulation in the high current range. You have a device, you have a constant current source. Okay, you can set in low current range. Now what you need is you need a decade resistance box that can carry a current of 1 ampere. So we need a decade resistance box which can give us these resistances 100, 200, 300, 400, 500, 1000 kilo ohms. Okay, we need 2 digital multimeter, 1 digital multimeter in 20 milliamperes range to read the current, and we need another digital multimeter which gives us the voltage across the load resistance. So we have to now change the value of the load and we have to record the current and the voltage. So we have changed here 100, 200, 1000 and then up to 2000. You can see from this when the load changes from 101 ohm to 1001 ohm, the current remains almost constant. But when we change the load to 1101, the current decreases, and for 2000, the value of the current is very low. So this simple experiment will give you the feeling that how over a certain range of load resistance our constant current source will work. Okay, so this is for one current. Here the current is 10 milliampere. What in this experiment is readings for this particular reading? The current in the constant current source is 10 milliampere. We have varied the resistance from 100 to 2000 ohm. Okay, we measure the voltage and the current, and we repeat it. So this is the graph. Here you can see this upper one is for the data that I showed earlier. So here up to 1000 it becomes constant and then it decreases. So from this data we can find out that our CCS can be used over this range. Now you change the current. Experiment is repeated for another constant current of 5 milliampere. We reduce the current and we see that we can force the common current source to act over a larger resistance range as a constant source. Same thing we can repeat in case of decayed resistance box. We need now this is again DC regulation in a higher current range. So here we need a smaller resistance. So we need a resistance box giving us 1 to 55 ohm for these particular readings. Again we do the same thing. We measure the current, we measure the voltage, plot a graph, okay, and we can again confirm that this resistance, this is constant over here for one current, this is constant. If you change the current, we get a higher range. So once you perform this experiment, you will have a feeling that how the constant current source in low range and the high range can be used for one or the other experiment. The other device is DC differential amplifier. DC differential amplifier, as the name suggests, most of you will be of electronics background. Okay, so its function is to amplify the difference between the two signals. This is simply a block diagram. We have two inputs V1 and V2. The output is VO. So we can simply call a DC differential amplifier as a three-terminal device, two input and one output, and V output can be written as AD V1 minus V2. AD is called differential gain. Okay, operational amplifier. Basically, the basic electronic circuit which is behind the operational amplifier is nothing but DC differential amplifier. You must have read how DC differential amplifier can be made by using two matched pair of transistors. Okay, so here V1 and V2 are the two input signal. We get the output VO. So VO is equal to AD into V1 minus V2. But what we call something like a common signal, okay, a common mode rejection ratio. So there are two types of signal about which we talk about to understand DC differential amplifier. One is called a differential signal. Differential signal at V1 and V2 are basically out of phase. They are called inverting and non-inverting terminal. But if we have a common mode signal is nothing but it is an unwanted signal coming from the external interference. Okay, I will explain you what is that external interference. So common mode signal appearing at V1 and V2 will be in the same phase, but differential signal appearing at V1 and V2 will be out of phase because one is inverting and the other is non-inverting. So theoretically, the signal or the common mode signal, which is common to both the inputs, should not have any effect on the output voltage. Okay, because if we have a same signal at V1 and V2, at VO it must be equal to 0. But things are not that simple. Okay, this is a simple circuit in terms of transistor. So again, VO is AD into V1 minus V2. A common mode signal is the one that drives both inputs of a differential amplifier equally. The common mode signal is the interference, static, and other kinds of undesirable pickup. These things will be what type of noises are there. Okay, suppose we are performing experiment here, flicker noise, thermal noise, electronic noise, several types of noises are there, but those will be discussed in more detail by Prof. Srinivasan in the lecture on phase sensitive detection. Okay, so we have to understand the noise. Suppose the noise is there, how to get rid of that noise. Suppose we are getting some noise along with the signal, how to get rid of to perform the experiment. So the connecting wire on the input basis act like small antennas. If the differential amplifier is operating in an environment with a lot of electromagnetic interference, each base picks up, you must have read like this. Normally, if you just design an operation amplifier, a difference amplifier, by making use of two transistors, we are same in all respect. BBE is not of one transistor is not equal to BBE of the two. So that is why even if B1 and B2 both are the same, okay, because if you look at this equation theoretically, if B1 and B2 both are the same, the value of BO must be equal to 0. Or if we connect B1 to ground, B2 to ground, the value of BO must be equal to 0. But that is not the case. Even if here the value of B1 is equal to 0, the value of B2 is also equal to 0, BO will not be equal to 0. It is called offset voltage, and that is the problem. Okay, so practical effectiveness of rejecting the common signal depends upon the degree of matching between. If the two transistors are same in all respect, we will get rid of those common mode signal. But that is not the case. So therefore, we talk about in fact these two. One is differential gain, and other is common mode gain. So difference between the two inputs is V1 minus V2. Common mode signal is the average of the two. It is V1 over V2. And we can write down V1 to be equal to Vc plus D1 over 2. We can play with the two equations here. Okay, so these two equations, the difference and the average. So if you solve them, you get V1 and V2 in terms of Vc and Vd. Now we can write down the output voltage as A1 times V1 plus A2 into V2. V1 and V2 are here. So we can write down this as A1 minus A2 over 2 Vd, A1 plus A2 into this. So this is differential gain and this is common mode gain. The ratio of differential gain to the common mode gain is called common mode rejection ratio. Okay, theoretically the value of common mode gain must be equal to 0. So if the value of AC is equal to 0, the CMRR must be equal to infinity. So it basically larger the value of CMRR, more better is the circuit to reject the common mode signal. Okay, so common mode rejection ratio shows the ability of a differential amplifier to reject the common mode or unwanted interference. This is operation amplifier or a differential amplifier. B1, B2, Bs plus and Bs minus. These are for supply. Normally we use plus minus 12 volt. B1 and B2 are similar to the earlier picture. So B1 and B2 are the signal, B output. If the value of B1 is equal to 0, B2 is also equal to 0, the value of B output must be equal to 0, but that is not the case. We call it as the offset. So what we have to understand in the laboratory session or while performing experiment, how to get rid of that signal. Okay, so a DC differential amplifier here in the lab, it is used to measure the small DC currents of the order of microvolt to millivolts. That is one thing. Because we are using thermocouples to measure the temperature. Okay, thermocouples normally generate this much of the voltage. It is thermo EMF. We will discuss in more detail in the afternoon session. But normally the voltage that differential amplifier has to measure is of the order of microvolt or millivolt. Thermocouples measuring temperature difference of a few degree provides a signal. A DC differential amplifier can amplify a signal to 10 or 100 times. Here in the lab, we are using it in two modes. Either we are going to amplify the signal 10 times or we are going to amplify the signal to 100 times. So if we are getting 1 millivolt signal, it becomes 100 or 10 depending upon the amplification factor, and that we can measure easily by using a small multimeter. Okay, so in this experiment, the amplification of 100 will be used. Common mode pickup, common mode signal, it is very common if we are using a long thermocouple wire and that too in a noisy environment. Effects of common mode pickup can be minimized by using a differential amplifier. We will see just after this how. Thermocouples measuring temperature difference of a few degrees centigrade provides very small signal, and DC differential amplifier serves to amplify the signal and also reduces the noise. This is again an operation amplifier circuit. B output for this circuit is B output is B2 minus B1 divided by R3 over R1. If the value of R3 over R1 is 1, there is no, the gain is 1 because V output differential gain is 1. So we can change the value of differential gain just by increasing the value of R3 over R1 ratio. Okay, so in our device we have three choices. The value of R3 over R1 is 1, the value of R3 over R1 is 10, and the value of R3 over R1 is 100. So we can use it in three different modes, three different amplification factor, 1, 10 and 100. This is the DC differential amplifier. So here in this DC differential amplifier, this switch, okay, we have a on-off switch, we have a LED here that shows the status of our device. We have now this switch can be used in either 10 amplification. If it is in the middle, it will give three positions, down, in the middle and up. So down it is 10 cross 10, that means amplification factor is 10. In the middle, the amplification factor is 1, and if it is up, the amplification factor is 100. So we will use it for 100 amplification. 100 amplification will be 100. At the end, I will tell you how to ensure whether the amplification is really 100 or we have been told that it is 100 and we are assuming it throughout. Okay, so you have to perform an experiment just to ensure that your signal gets multiplied by 100 or not for that particular switch. Here we have basically three pair of switches, 1, 2 and 3. Here again we have three switches, L1, L2, L3. So if we are going to put this knob to L1, okay, it is going to amplify the signal across these two. If we put it to L3, this signal will be amplified, and across L3 this signal will be amplified. So we can measure three different signals by using this DC differential amplifier. Okay, what we have to do? We have to simply play with the knob here. Okay, in the next experiment that I will discuss after the lunch, thermal conductivity of copper, thermal conductivity of perspex, and electrical conductivity of copper, we are making use of all the three terminals. So we are using amplification of 100, and just by selecting this knob, okay, we can change the output. Normally when you will go to the lab, it often happens that you have to measure the voltage across this, but you don't change this knob, so be careful. Okay, then we have an offset knob here. Offset knob means, suppose we are not connecting any signal, suppose both the terminals are grounded, you have to check the offset also. First of all, you have to connect this to ground and this also to ground. Okay, so therefore this is the output. So output is normally measured by a digital multimeter in the millivolt range. So we are going to connect a digital multimeter here. Whatever is the signal here, it is amplified by 100, and we read it from by using a multimeter. Suppose we are not using any signal here, so we expect that our multimeter should read 0. But that is not the case, that is called offset. So what we have to do, we have to connect these terminals to ground, then we have to have a multimeter here. Now we will play with offset knob. So we will minimize the offset. It will not be equal to 0. If it is 1 millivolt, 2 millivolts, 3 millivolts, it's okay. So we have to reduce it to 0. Okay, close to 0. And then now there is a switch called reverse switch. The reverse switch means the signal here is reversed. Okay, so suppose our signal is 10 volt, so it will now become minus 10 volt. So we have to, every time, we have to measure the signal first by putting this down, okay, and then up. One is a normal signal and the other is reverse signal. What we expect is, because the beauty of taking those three readings are that when we reverse the switch down, the signal gets reversed. But the noise, that is unwanted interference, the pickup, that will not be reversed. So pickup will remain the same. Okay, our signal will change its polarity. So we have to, so in the beginning, first of all, we are going to connect these to ground. Okay, by making use of this knob, we are bringing it to minimum. Okay, and then we again reverse this. Normally, object should not change sign. In some cases, I am telling about 1 millivolt. In some cases, you are getting about 11 millivolts also. But if the minimum is 11, you leave it there only. Okay, that will not change your signal. That will be clear in the next transparency. So here, suppose we are going to take this one. So there are three pairs of the same thing that I explained, three pair of banana terminals marked I1, I2, I3 on the bottom of the front panel, to which three different sources of EMF can be connected. A selector switch at the center of the panel allows the selection of any one of these terminals. A toggle switch to select the amplification of 10 or 100. A part marked offset to adjust the offset of the amplifier to within a few millivolts of the zero. Okay, a selector marked reverse is to reverse the connection of the source EMF. One way is you change the bias like this, but there is a switch. So switch automatically changes the signal. A pair of banana terminals marked OP, that is output, is there to measure the output by connecting a digital multimeter in the appropriate DC voltage range. So adjusting the offset, I have already explained that you connect both to 0, okay, and adjust the offset to 0. It should not change, it will not change the magnitude, and reading will remain the same even if you reverse the signal. Let us see how we get rid of. Suppose now we connect the signal, connect the source EMF to be measured to terminal 1. Set the DMM in the appropriate range and note the reading. Now what we are going to do is, our signal is now B signal. This is our signal. By using DC differential amplifier, we are amplifying it 100 times. So our signal becomes 100 times B signal. That is what we expect when the switch is up or down. Suppose it is up, so it is B plus offset will be there, the noise will be there. So signal 100 times the signal plus offset. Now we put the switch down in the reverse mode, so signal becomes now B minus. So therefore B minus becomes minus 100 B signal and offset will remain the same. So we are taking the reading when the offset knob is up, we are taking the signal when the offset knob is down, okay, and now we subtract one from the other. So if you subtract, this becomes 100 into 100 into B signal. So if you add the two and divide it by 2 and divide it by 100 also, because 100 is the amplification factor. So B signal will be equal to B plus minus B minus 2 into 100. In some cases, if you are reversing the signal, suppose you are measuring minus 15 millivolts, you reverse the switch, the reading comes out to be minus 65. Then also you need not to worry about that, means the noise is very large. Okay, but by doing this, you throw away the noise. Okay, so suppose you are there on the experiment, and you are in hurry, you are not going to check the offset. Okay, the instrument is given to you, you start measuring the things, and the offset, and at the end of the day, you measure the offset. Suppose it comes out to be minus 15 millivolts. So one thing is you repeat the experiment, and the other thing is, without worrying much about the readings, because you are going to subtract it, even if the offset is large, you minimize from your end. Okay, because reading after changing the switch must become positive or negative. It is initially positive, it should go to negative. But sometimes it's positive to positive or negative to negative. That depends upon the large offset. So this B signal is B plus B minus divided by 2. So thus the reversal switch is to just throw away the offset voltage. That is the beauty of this. Suppose B positive comes out to be 10.9 millivolt. We reverse the switch, B minus comes out to be minus 9.1 millivolt. So our signal is 100 millivolts. Okay, we divide it by 2 into 100, so it is 100 millivolts. If the signal of the output does not change on toggling the reverse switch, it means that the offset voltage is larger in magnitude than 100 times B signal. That is what I told you. One can turn the offset part so that the two signals are of opposite sign. In the beginning itself, what you can do, you can play with the offset knob, that on one side the signal must be positive, on the other side signal must be negative. So that will basically take care of many things. Okay, these are all the three terminals. They can be used simultaneously. Okay, offset will not change. offset will remain the same for all the three terminals because you have three choices of measuring EMF. So once you set your offset to minimum, okay, it will remain the same for all the measurements. Now suppose you want to check whether the amplification factor of DC differential amplifier is really 10 or 100 or not. So there is a calibration box that is also provided, you will find in the lab. It is calibration circuit for DC differential amplifier. Okay, we have a on-off switch, we have a battery 1.5 volt inside this. It is in series with a high resistance and this is a potentiometer. It's a pot. You can vary it. So by varying this, you can have some voltage here. You can have some voltage here also. Okay, so the two pairs of other terminals on the box give the voltage across the potentiometer. By adjusting the potentiometer, one can get any voltage from 15 millivolts upward at the terminal T1. When the switch is turned on, a light glows indicating the charge state of a cell. That is all about the cell, whether you get the voltage or not. Otherwise, if the cell is not charged, you will not get any voltage. So what you have to do, you measure this voltage. So it is 15 millivolts. Suppose it is 15 millivolts. So you measure by multimeter, it is 15 millivolts. Now you take out two leads connected to our DC differential amplifier, to I1 or I2 or I3. Let us say it's I1. So now you measure the output by using another digital multimeter at the output terminals of DC differential amplifier. This 10 volt must be equal to 1000 volt because 100 times amplified. So you can do this also. It will not require much time, but you can, if you do this, you will just ensure that the gain, the 100 gain or 10 gain that you are using is really 10 or 100 or not. So these are the small things that you can do in the lab. If you are using T1, so T1 100 times, suppose you are using T2, T2 is basically 1/10 of a voltage. Because if you want to measure 10, 15 into 10 will become 150. But suppose you want to measure the small voltage, so there are two terminals. T2 gives a voltage that is 1/10 of a voltage as T1. You can do the same thing. You take out the voltage from T1, feed it to DC differential amplifier, amplify it to 10 or 100 times, measure the output through DMM, okay, and just ensure that 100 written on the box or 10 written on the box is 10 or 100 or not. So that is all about these two experiments. If you have any doubt, we can discuss.
In this case, you have neglected the internal resistance of the transistor.
In which case?
Making the DC
DC amplifier. No, DC amplifier is basically made by using. In fact, if we start in the beginning, normally once the transistor discussion is over, then we discuss about transistor amplifiers, then DC difference amplifier. So in fact, DC difference amplifier, suppose we want to get rid of or we want to have a very good common mode rejection ratio, the two transistors must be same in all respects. Okay? So in the beginning I said BB of BBE means base emitter voltage of one must be equal to base emitter voltage of the other. If you see the expression for base emitter voltage depends upon several things like intrinsic carrier concentration of things. It depends upon the width also, width of the basically layer, and it's very difficult. 110 angstrom is very difficult to control. So if the width changes by 1 angstrom, the value will change. So it's impossible. You purchase basically two transistors manufactured under the same conditions, so they will differ. So since BBE and BB, otherwise theoretically the common mode rejection ratio will be infinite. So we are not talking about the resistance, other things. I simply wrote a formula that B output is equal to B2 minus B1 into R3 over R1. Okay, I am sorry to tell you that I can't derive that formula. I simply copied it because from there I can explain you that by changing R3 over R1, we can change it to 1, 10 and 100. 1 is not required because 1 means no amplification. So just 10 and 100, so we can change the amplification. Matched pair of transistors, in fact, you study because normally in textbooks we say those two transistors are the same. Okay, but please study about matched pair. What do you match? Okay, why the matching is impossible?
The beta value will be different.
beta value will also be different. Beta will also be different. So the beauty here for this particular lab, okay, the beauty is that you can measure the voltage, you can increase signal to noise ratio. You are going to throw away the noise, okay, just by reversing the switch. You reverse the switch, the signal gets reversed, but the offset remains the same. So you take one, in case of one, you are going to take two readings. Now you take the difference, so offset goes away and divide it by 2, so you take the average, so offset is minimized. That is the beauty of the experiment. So one beauty is offset goes away, and the other is we can measure small signals. Otherwise the problem is, suppose we have a copper transmitter thermocouple, the output is very small. It's a 40 microvolt per degree centigrade. That means if I increase the temperature by 10 degree centigrade, it is 400 microvolt. 400 microvolt means 0.4 millivolts. So if you use a multimeter, it's very difficult to get 0.4. But if you are using this DC difference amplifier, 0.4 becomes 40, 100 times, and 40 can be read by a multimeter. That is the beauty. In fact, all these things they have been developed by the Prof. Srinivasan said. So all these circuits are basically his own circuit. He has developed and given into Ajay sensors. Ajay sensor basically just he is there to just make compact instrument. Rest of the things you will, when you will go to the lab, I think then things will be more clear. Okay, so I will call now Professor Srinivasan for the second.